Hi there, welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're looking at how you can prove trigonometric identities using Mois' theorem, and how you can use what's called Z notation to calculate identities for powers of trig functions. But first of all, we'll look at the expansions of cosine of some multiple of theta or sine of some multiple of theta, where you're finding those in terms of cos theta or sine theta by using Mois' theorem. Now I'll do an example with you and things will become a lot clearer. So for example, if you had to use Mois' theorem to prove the double angle formulae for sine and cosine, that's sine 2a equals 2 sine a cos a, and cosine 2a is cos squared a minus sine squared a. The way we'd prove those is we let r equals 1, and on these questions we always let r equals 1, and the value of n that we use depends on what we're trying to find. If it's sine 2 theta, we'd use 2, sine 3 theta, we'd use 3, cos 5 theta, we'd use 5, and so on and so on. Anyway, putting r equals 1 and n equals 2 in, we'd get cos theta plus I sine theta squared is equal to cos 2 theta plus I sine 2 theta using Mois' theorem. What we then do is expand this bracket on the left-hand side, which gives us cos squared theta plus 2i cos theta sine theta. We get minus sine squared theta because we've actually got I sine theta squared, and the I squared gives us minus 1. What we then do is equate either the real parts or the coefficients of the imaginary parts. Now, if we equate the real parts from both sides, on the left-hand side we get cos squared theta minus sine squared theta, and on the right-hand side we get cos 2 theta, which immediately gives us the double angle formula for cos. Cos 2 theta is cos squared theta minus sine squared theta. If we equate the coefficients of the imaginary parts, then on the left-hand side we get 2 cos theta sine theta, and on the right-hand side we get sine 2 theta, which again immediately gives us the double angle formula for sine 2 theta. This is a surprisingly powerful method for deriving this type of identity. Anyway, I'll let you have a go at doing one yourself. So using the method above, try and prove that sine 5 theta is equal to 16 sine to the 5 theta minus 20 sine cubed theta plus 5 sine theta. The method is exactly the same as the one we used there, but it is quite a lot harder because we have 5 theta now instead of 2 theta. But have a go yourself, pause the video and come back to me when you're ready. Okay, let's have a look at this together. So that's what we're trying to do. We always let r equals 1, which gives us that. And in this question, we'll let n equal 5 because we're trying to find sine 5 theta. That gives us that, and that's using Mois' theorem on the right-hand side. We then expand these brackets. This time we do need to use the binomial expansion. To find the coefficients, I would always use Pascal's triangle unless the number is ridiculously big. And because it's a power of 5, those will be the coefficients, 1, 5, 10, 10, 5, and 1. And the pattern is that you start off with cos to the 5 theta, if you're taking cos from each of the 5 brackets. And then the powers of cos go down by 1, the powers of sine go up by 1. The coefficients are just these numbers, but we do need to be careful with the i's. So when we have sine squared, for instance, we'll actually have I squared sine squared, which is why we get this minus here, when I squared is minus 1. When we have sine to the 4, we'll actually have I to the power of 4 sine to the 4 theta. And I to the power of 4 is plus 1, which is why this returns to plus here. And for each of the other terms, you do just need to walk carefully where I is concerned. So that's what we've done so far. That's the expansion of the brackets on the left-hand side. And here we have what we did using Mois' theorem on the right-hand side. We've been asked to find sine 5 theta. Well, sine 5 theta is tied up in the imaginary part here. So it's the coefficients of the imaginary part that we're going to have to look at. If we wanted to know what cos 5 theta was, then we'd be using these black terms instead, because all of those are the real terms. But we need the imaginary ones, and we'll look at their coefficients and equate them on both sides. That gives us this. Now, on the last question, that was the end of the question. Sadly, it's not this time. If you go back to what we're asked to do, it's to write sine 5 theta purely in terms of sine theta. There are no cos thetas here at all. So we do need to get rid of this cos to the 4 from here and this cos squared from here. The easiest way to do that is using cos squared theta is 1 minus sine squared theta. And that'll give us 5, and then we'll have 2 lots of cos squared there and 1 lot there. From here on, it's just multiplying out brackets and collecting terms. As long as you don't make any mistakes, you do get exactly where they asked us to get in the end, which is that sine 5 theta is equal to this expression. Okay, what we'll look at now is how you derive expansions, not of multiples of theta, but powers of cos or powers of sine, using what's called Z notation. And we let Z equal cos theta plus I sine theta. That means Z to the power of minus 1 is that to the power of minus 1. Using de Moivre's theorem, that gives us Z to the minus 1 is cos minus theta plus I sine minus theta. Then using a trick that we've used several times before, we can change these minus thetas to plus theta. There's no problem with the cos because cos theta and cos minus theta are the same. But with the sines, you do have to change the plus to a minus because sine theta is equal to minus sine minus theta. What we then do is add Z to Z to the power of minus 1. So we're adding Z to the reciprocal of Z, to 1 over Z. And if we add them together, the I sine and the minus I sine cancel, and we just have 2 cos theta. If instead of adding, we subtract, then if you subtract the reciprocal of Z from Z, then the real parts cancel, and you get 2I sine theta. Be very careful. It's easy to forget the I here. So you get 2 cos theta when you add them, but it's 2I sine theta when you subtract them. Don't forget the I. Similarly, if we look at Z to the n, Z to the n is cos theta plus I sine theta to the n. Using de Moivre's theorem, that's cos n theta plus I sine n theta. Z to the minus n will equal cos minus n theta plus I sine minus n theta. Using the same trick that we used just now, that gives us cos n theta minus I sine n theta. Adding those together, so if we add Z to the n to 1 over Z to the n, we get 2 times the cosine of n theta. If we subtract one from the other, Z to the n minus 1 over Z to the n, again we get 2I sine n theta. Don't forget the I. That's just a summary of what we've done. I possibly make a very quick note of those and refer to them as we go through the rest of the lesson. Okay, how do we use them? Example 2, find cos to the power of 6 theta in the form a cos 6 theta plus b cos 4 theta plus c cos 2 theta plus d. So this time we're finding a power of cos in terms of multiples of theta and cosine. Now, I'll let you have a go yourself. It's very difficult to work out exactly what's going on in these questions when you've never seen one before. But if you'd like to have a go, then do so. Pause the video and come back to me when you're ready. Okay, I'll go through this with you. If you manage to get to the end by yourself, then very well done indeed, because there's a few steps where you need to work out exactly what's the best thing to do. Anyway, Z plus 1 over Z is 2 cos theta. Z to the n plus 1 over Z to the n is 2 cos n theta. We stated that just now. Because we're finding cos to the power of 6 theta, what we will do is find Z plus 1 over Z to the power of 6. Now, Z plus 1 over Z is 2 cos theta, so that's 2 cos theta to the power of 6. And 2 to the power of 6 is 64, so that's 64 cos to the power of 6 theta. And then we do something very similar to what we were doing on the other questions, which is we expand this bracket using the binomial expansion. So we're doing Z plus 1 over Z times by itself 6 times. This time we're going to need to go down to the row in Pascal's triangle, which starts 1, 6, then 15, 20, 15, 6, 1. Those will be the coefficients that we need. Multiplying those brackets out, the first term will be z to the power of 6 when we take z from each of the 6 brackets. When we take z from 5 of the brackets and 1 over z from one of them, then that is what we will get. And so on and so on. The powers of z go down by 1, the powers of 1 over z go up by 1. Okay, that's what we've just done. The next thing that we do is we multiply out. So z to the 5 times by 1 over z just gives us z to the 4. Z to the 4 times 1 over z squared gives us 15z squared, and so on and so on. So we just multiplied out the brackets. That gives us that. Now it's this next step that's a little bit tricky to guess if you haven't seen it before. We pair the terms up. We pair z to 6 with 1 over z to the 6. And we pair the z to the 4 with the 1 over z to the 4, and the z squared with 1 over z squared. And you'll notice they have the same coefficients, which does help with the factorizing, and then plus 20 added on the end. The reason why we do that is we're now going to use this expression, that z to the n plus 1 over z to the n is equal to 2 cos n theta. So using that on each of these expressions gives us 2 cos 6 theta plus 6 times 2 cos 4 theta plus 15 times 2 cos 2 theta plus 20. Multiplying out the brackets gives us that. Now, we found z plus 1 over z to the power of 6 in 2 different ways. Using de Moivre's theorem, we found out that it's equal to, no, it's not using de Moivre's theorem. It's just using this expansion for z plus 1 over z. So using that, we found out that it's equal to 64 cos to the power of 6 theta. And then by multiplying out the brackets, we found that it's also equal to this. So these two things, they are exactly the same as each other, which is what we've written here. Now, we wanted to find cos to the 6 theta. We're very nearly there. We've got 64 cos to the 6 theta. All we have to do now is divide through by 64. And when we do that, we get cos to the 6 theta is equal to this expression here. And that is the answer. So A would be 1 over 32, B is 3 over 16, C is 15 over 32, and D is 5 over 16. Okay, the last example, and this is fairly quick, you'll be glad to know. Use your answer to the previous question to find the integral between 0 and pi over 2 of cos to the 6 theta d theta. There is no easy way to integrate cos to the 6 theta. The only way that I know is using what we just did in the last question, which is that cos to the 6 theta can be written down like this. Once you do that, it's fairly straightforward. I'll let you have a go yourself first at finishing this off. So pause the video and come back to me again when you're ready. Okay, well, the integral immediately changes. So instead of integrating cos to the 6, we find the integral of 1 over 32 cos 6 theta plus 3/16 cos 4 theta plus 15 over 32 cos theta plus 5 over 16 with respect to theta. So that's the integral that we're going to have to do, and we just take it one step at a time. Integrating the first term will give us 1 over 192 times sine 6 theta. Integrating the second term gives us that. Integrating the third term, that. And integrating 5 over 16 gives us 5 over 16 theta. Now all we have to do is put in the two limits, and thankfully they've chosen very friendly limits. If we put in pi over 2 first of all and then 0, nearly all of the terms are 0. The only one that isn't is when you get 5 over 16 times by pi over 2, but all the other terms are 0. So that does simplify to just 5 over 32 times by pi. Okay, that gets us to the end of this lesson. If you have the textbook, turn to page 35 and have a go at exercise 3D. Thanks very much for listening, and cheerio.